Hey everyone, we will start on top of the hour. Welcome. Thanks for coming. And if you want, in the meantime, to check out the paper, I put the open access link, like from our Google Drive, in the chat. And on top is the presentation. So in the meantime, feel free to check out what we will be talking about today. Thank you. Hi, Diana. Good day to you. I know it's not morning for you anymore, so how are you today? To unmute, it's all the way on the bottom right. There's a little microphone symbol. If you press on that, you should be able to unmute. Diana, can you hear me? If this doesn't work, please, if you're at the university, don't use the Wi-Fi. That sometimes works. Okay.
Now,
yes,
hello?
perfect.
Yes, now, yes.
You
I
were
couldn't
on the
hear.
Wi-Fi of the university?
Yes, I was on the Wi-Fi.
Yeah, I'm sorry.
Strange.
Most universities, they block, like you can log in, but you cannot hear or speak. And
Okay, okay. First time I see that, but good. Good to know. So you hear me well? I have
yes.
some noise, but this is the laboratory pumps right now. Unfortunately, I have no more quiet.
Oh, don't worry about it. We can hear you well, so that's good.
Okay.
How are you? We still have a few minutes, so you can
So
relax.
how is this working exactly? The because I guess it's discussion. Is people asking questions, or because I have no real access to the presentation, I don't know, I should follow the slides or...
Yeah, so the presentation, if you see, for the audience is linked
Yes.
on the top of the room, so above our icons. There's a link
Yes.
that people can click, and there's a presentation, but people have, it's not a screen share, so
Okay.
people have to follow along on their own pace. So it's really helpful if you refer to on which slide you're on when you switch. And
Okay.
then in general, I will in a few minutes introduce you and ask you a couple of interview questions, and then you
Okay.
can present your slides and your work, and then we'll open it up for questions. That's how it usually works, but if you're
Okay.
open to also
Okay.
have
Okay.
questions during the presentation, that's also good. Like whatever you decide is good for us.
This maybe seems in this case the people should follow the presentation by themselves. It's better if they have questions to ask on the moment, because some of them might be on the wrong slide, or I guess.
Okay. Yeah. Good. Perfect. Thanks for doing this. Coming on here, making the accounts. We really
No,
appreciate it.
thank you for inviting me. It's first experience. I hope I will be able to interact with people as expected.
Yeah, for sure. It will be fun. So just relax. This is, supposed to be fun and, informal, and
Okay. Okay.
will be
Sounds good.
all good. Meet Frank. Hi, Frank. How are you today? Thanks for coming.
Hi, Karina. Hi, Diana. Thanks for coming to share with us your great research. I'm looking at the slides. It's so interesting. So I'm really looking forward to thing.
Well, thank you. Thank you for inviting me.
Just out of curiosity, you mentioned the background noise is from some equipment in your lab.
Yes, it is.
Well,
So I may try to move eventually, because I see it's gonna be a bit difficult to stay here.
no,
Let's see.
just curious. What type of equipment is that? Like making the chirping
This
sound.
this is a dye pump for a laser. So it's a laser with liquid as a medium, and it has as a pump. Pumping all the time makes this high frequency noise, and it's the only equipment running now. But normally we have many noisy equipment at the same time. It's quite it can be quite perturbing at moments. But then we just go remotely to the office and run the experiments from distance, let's say. Now I was preparing an experiment, so had to be in place, let's say. But now I
I
guess it's
see.
quiet. It's quieter, I hope. Is it?
It is, yeah.
Yeah, I just got out. Yeah, 1 minute.
Okay, perfect. Yeah, I think we can slowly start. People will come in more since it's pretty early in the US, and but the good thing is we record this so people can listen to this afterwards, for on the West Coast and so on. So I think we can just start. So welcome everyone to the Science Society, and of course a special welcome for Diana Serrano. Thank you so much for coming here today and share your really exciting and really interesting research here with us. But before we start, let me introduce you to the audience so they get to know you a little bit. So
Yeah.
Dr. Diana Serrano, she's a researcher at CNRS in France, and she did her bachelor of arts in piano at the High Conservatory of Music of Castilla, Leon.
Right?
And
Yes.
that's amazing. A friend of mine, he was on our PhD. He did the same. He also was a great musician, and then also did his PhD with us. So interesting. He's from Montpellier, but anyhow, and then she did her 5-year degree in physics uh, with a master included at the University of Salamanca. And then she did her PhD in physics in optics and material at the Center. I can, I'm
Yeah,
very
it's in
bad at
French,
French.
yes.
At the Centre de Recherche
You
de
can just
Sur.
translate.
Yes.
It's
At the
a
University in the Normandy, Bas, and her thesis title was Quantum Cutting Processes in Rare Earth Doped Fluorides for Photovoltaic Applications, under the supervision of Dr. Alain Broad and Dr. Richard Moncourt. And then
Mucose,
she,
yes.
oh, sorry, I'm so sorry.
No, that's fine. That's fine.
And she did her postdoc then at the Lund University in Sweden. And then she went to the University of Zurich in Switzerland with Stefan Sergers. And then now she is at the CNRS in Paris, continuing her research. And it's so interesting that you first did a music degree and then you went on to do research. So was it always a dream of yours to become a scientist, or was it something, did something happen when you, after you finished your piano degree, like a teacher or class or something that fascinated you, that you decided then move on to science?
Yes, it's a very good question because many people is puzzled by this maybe a typical path. The thing is, I started studying music really when I was very young, as a child. So it's the kind of things you start when you are 5, 6 years old. And then by the time it was time to go to university, I was pretty much aware of what being a musician was because I had been doing this for 10 years back then and doing some competitions and taking this very seriously, almost professional. While on the science part, I was just a high school student, so I had no idea what to be a scientist was back then. But I was a good student too at school, so I couldn't make my mind by 18 when I had to go to university and doing this music degree, and I decided to do both at the same time, and which was quite crazy, I have to say. But well, finally, I managed to survive this double degree simultaneously. And as I progressed on the physics side, I got more into it and I enjoyed more. And yeah, somehow I finished and I said, okay, let's take a break on the music for 1 year first in my life, and then just finish the physics degree. And it all followed. Like I was proposed to continue on the PhD, then I went on the PhD, and it just evolved by itself, let's say. So I didn't make my mind very early about science. It just happened progressively, and I guess that was a good choice.
Perfect. That's wonderful. Do you still play piano a lot, or do you still make music? Do you have time?
Well, I do it for fun. Of course, I do it in a very, very low rate compared to back in the time. I do it really as a amateur, if I may say, with a band, a little bit of more jazz music, more than classical as I used to do, but for fun, with no pressure. No, I really don't have much time, to be honest, to keep that at
That
the level, but
Yeah,
it's fun.
that's wonderful. I think it's good to not burn out, to,
Oh yes,
to
of course.
have
No,
a, to have something else also. That's wonderful. And how did you come to then decide to work in this field? And is there maybe like a story about this specific project? Was it, easy to get funding for it, or how did you get to work in this project? And this,
Yes,
yeah.
so it's another interesting question. It was when I started my first contact with research. Indeed, is when I moved. I was finishing my bachelor in Salamanca, and is when I finished the piano studies. I took 1 year abroad. This is very typical in Europe. Is this Erasmus program that the European students are going to another university for taking some courses while still enrolled in the original university. So it was my first year of freedom, let's say. Last year of studies, I went to France, to Normandy, for finishing my studies, and there I was offered to join some practicums in the research labs they had there. And then the lab, there were several options like nuclear physics and other fields and solid-state physics, and there was a lab doing these photonics projects. I kind of like it, and then it was the first time I saw this kind of research, because in my university in Spain they had not such topic at all, so I had never seen this in the lab. And then it was first contact for me. I really like these materials, these lanthanized rare earth ions, and decided to continue with them. But back in the time, I was doing more classical applications, let's say, was similar type of materials, but the application was more for photovoltaics, optoelectronics, other kind of things. But this quantum field was starting back then. It was still very, very minor when I was doing my PhD. But I already saw it could have, sorry for the beep, it's like still one equipment beeping. Still saw it could have quite some future 10 years ago. And I decided to go on a postdoc and start to look at that in my first postdoc in Sweden. And then I definitely like it a lot. So when I finished that postdoc, I moved to Zurich. I did a little bit of medical research to try another medical. It's still optical spectroscopy stuff. It's not like I changed to any medical things, but let's say the final application was medical, because it was another field I found interesting. And it was then when I thought, like, no, I really like the quantum stuff I did in Sweden. So when I will propose a project to join the CNRS, like I'm now, will be on that field. And then is when, let's say, when I decide what was the field I wanted to work at, following these experiences. Can you hear me?
Well, I'm glad. Yep. Thank you. Thank you for that story. And I'm so glad you got to work into what you really like and what you're curious about. It's such a,
That was very lucky. Yeah, I had this opportunity.
yeah.
It's not
So
always the case, that's for sure.
that's wonderful. So congratulations, and congratulations to this amazing work. And yeah, the stage is yours now for presenting your really interesting work. So everyone, the presentation is pinned on top of the room. Feel free to follow along. And yeah, we're looking forward to it, Diana. Thank you.
Yes, so everyone is free to ask questions during the presentation. So these slides are actually scientific slides from conference, let's say, so they can be quite sometimes specialized. So don't worry if you find them difficult. I will really try to avoid the too much technical details to make it a little bit more easy to digest. But if I go to something which is not possible to follow, please let me know, and I will correct. So let's start. Let's see. I will open the presentation myself to guide. So this presentation is related to this paper published in Nature last year that you must have on the link. It was a research work which attracted quite some attention when it was published, and the reason is because we propose a new material system for for quantum technologies. And this material system is the rare earth molecular crystals. So those materials aren't new in themselves. So they have been used for other goals. They are known from the 60s, but they have never been looked at in this quantum applications perspective. And when you look at quantum applications perspectives, there are several aspects you have to really prove valid to say, okay, this is a good material for quantum hardware. So in my slide number 2, what I present is what are the requirements for quantum hardware. So when you're a scientist trying to develop materials for quantum computers, quantum repeaters, and all these kind of applications, there are 4 elements you have to take into account. That is the ideal, let's say, wish list. The first one is you would like to have a system where you can store quantum states. And these quantum states is 2-level systems. That's what I represent. So those are the 2 quantum information unit states, the 0 and 1. And we want to be able to create superpositions on these states. And this is what we call the long coherence time, or long T2 in the specialized field. So it's that those are very often spin states, is what I represent by this symbol of a ball with an arrow that represents a spin, but can be also optical states. So it's any 2-level system where we can create superposition state, and that this superposition state can live for a long time, would be in principle valid for quantum applications. So the next point, if you move to the next slide, is that we want our quantum states to be able to interact with each other, because we want to create quantum gates. So if we want to do computing, we'll need to do some interactions between the quantum information units. A third criteria is if we want to connect our quantum processing units with each other, we'll need some kind of optical interface, because quantum communications come through light, just as classical communications. So we have these optical fibers connecting our computers around the world. So for the quantum computing distribution is going to be the same. So we need a system which can interact with light, but in the quantum regime. And the fourth criteria is that if we want to do all these quantum state preparation, interactions, gates, and readout in a very efficient way, we are going to need some sort of photonic structure that enhance the light matter interactions. That's what I mean by integration. I'm right now at slide number 5. So these are our 4 criteria, but in practice, to have a material system which verifies all of these criteria at the same time is very difficult. And the proof is that nowadays research on this field is looking at different solid state systems like diamond, the quantum dots, those materials, rare earth materials I work with, but there is not the perfect one. They all have advantages, but also have things missing on this list. So that's why I guess most of researchers in the field for a few years now realize that it may be a good idea to start combining material platforms, trying to merge the advantages of several systems together, trying to go as close as possible as to this list I just presented of characteristics. And this is what this work was about in this paper. So we propose to merge 2 material platforms. One is what we call the rare earth crystals for quantum technologies, and the other one is the molecules. So these 2 material platforms, at slide number 7 right now, the presentation, are investigated individually. Like every one of them have enough interest to be looked at individually, but what we thought is if we can combine them, that may be even more interesting, and we could be able to have even better properties for the final application. So concerning the rare earth ions, this is my field, so my background field. I've been working with rare earth ions now for many years. So they are investigated in the context of quantum technologies because they can create these quantum states, so we can create quantum states on rare systems, on both on the spin states and also on the optical states. So this always happens at very low temperature. This is, let's say, a little bit of a drawback of these materials, but the quantum states, sorry, because there is a little bit of noise. There is no teaching room here. I'm sorry. What are you looking for? Yep. Sorry for the interruption. So I said is that we can create quantum states that are extremely long-lived. So they have the absolute record of lived quantum states, the rare earth crystals. In particular, we have a paper from a few years now which demonstrated that in a rare earth crystal we can create quantum states which can live as long as 6 hours. So this is an absolute record. They also have the advantage of present optical access. So if you remember my list before, I said we want to create quantum states. So this we can do in the rare earth crystal. 2, we need to interface our system with photons, with the light. And with rare earth material, this is also possible. So we have lots of optical transitions in the rare earth ions. And they cover several wavelengths, so from the visible to the infrared. And this includes a transition which is the same we use currently for telecommunications, which happens at 1.5 micrometers. And well, more, let's say, is not as important as the 2 previous points I mentioned, but not uninteresting, is that those centers are very, very stable, so they don't bleach. We can use them again and again and again, and the material remains very, very stable. So it's not, let's say, its degradation on time is negligible, which is not the case with other emission centers. They have, however, I would say, a difficulty. So all the people working with rare earth ions face a main difficulty is that those centers do not emit too much light. So they emit with a rate which is low, and it makes working with single rare earth ions quite difficult, because a single rare earth ion emits few photons per second. And even with the best detectors we have nowadays in the market, that can be very challenging if we really want to use these for real application. However, to really overcome this difficulty, there is a lot of work on integrating the rare earth crystals with photonic resonators. It's the 4th point I mentioned before, to be able to enhance these transitions. So the other material system we have here, which before this work, to be honest, I didn't know that much about, it was the molecules. So there's a huge scientific community working with molecules for quantum computing, quantum communications. So the molecules, I divide them in this presentation in 2 types. We have molecules which have spin states. So quantum state, it's states in the spin levels, which can be very long-lived. And other molecules which have optical transitions, which are basically the organic molecules. But they don't have both at the same time. So while the rare earth ions, we can have at the same time optical transitions and spin transitions, the molecules, typically we are going to have one or the other one. So this is not so good in that sense. However, they have other advantages, of course. That's why we are interested to them. The production, the way we synthesize this kind of molecular material is much less heavy, so to say. When we do rare crystals, we do this at super high temperatures in a melt at around 2,400 degrees. It's growths, crystal growth will take many, many days, even up to months, depending on the size of the crystal. It's high cost also. They cost a lot of money to be produced. And they have also the point that when we put our rare ions within the crystal, they are randomly positioned, especially. Let's say we have some doping level, but we don't know where the ions are with respect to each other. While in the molecular materials, we have way more control and flexibility to really do a material, a custom material, where we do a single layer of molecules, where we know at which distance they are located with respect to each other, where we know, for instance, which are the ligands, the exact atoms around our active ions, and so this is all around the chemical engineering, and gives much more possibilities to customize your material really and its spatial location. So this is, of course, of great interest if you want to do a quantum processor where you want to control the distances between your qubits or your quantum information units. So our idea here then was, okay, then let's take a rare earth ion with all the good properties a rare earth ion can have, and let's put it on a molecule, in the center of a molecular structure. So that's what we did. And then the molecule we are going to present was synthesized with the root is presented in slide number 12. So it's a molecule which has a single rare earth ion in the center and is coordinated by oxygen atoms and aromatic rings, carbon rings around. It's pretty classical structure for molecules. And it crystallizes actually, so it forms a solid state material, can crystallize. So the crystal structure is shown in slide 13. So it has a crystal phase we call monoclinic within the crystalline structures. And the European ions occupy a site within this crystal of a symmetry we call C2V. So it's important to know that the rare earth ions, they have, in particular, European has to be at a pretty low symmetry. So it means that the surrounding of the ion has to be a relatively low symmetry to be able to emit light. If it has a very organized structure around it, it will not emit light at all because of some what we call the transition rules, and they are forbidden. But when we have this relatively low symmetry, it emits lights. So this is a concern every time we put rare earth ions in a material. So in this case, there is no problem. We have a symmetry which is low enough. And then you see what our material looks like. So it's a network of molecules, totally organized, and the minimum distance between two European ions from molecule to molecule is around 10 angstroms. So that's pretty good. So this is a distance which is good to have this kind of quantum gates we are aiming at, but it's not too short, because having too short distances can also be a problem, because the ions tend to perturbate each other, and that can really limit your applications too. So 10 angstroms is a good compromise, let's say. So what we did, this material, this synthesis was inspired from a synthesis done in the 60s. So it was done by collaborators of us, which are currently in Germany. But we didn't know much about this compound, so we didn't know where the optical transition was, what was the lifetime of the levels. We basically had to study everything from scratch. So we started by studying the luminescence properties of this material. So what you see in slide number 14 is a typical emission spectrum. So emission spectrum from europium. We recognize the lines, we can attribute the transitions of these lines, and the small transition, which is shown in red, which is actually very small compared to all the other ones, is the one we would really want to exploit for quantum applications. Then you see that the centers are really stable. As I mentioned, rare earth ions are expected to be very stable. So that's the photostability measurements shown also in the slide number 14. And if we zoom now on the transition we want to use to store quantum states, this one is shown in slide 15. Is the European 5D07FO transition. The peak wavelength is 580.3779 nanometers. This was something we had to find out ourselves. We didn't really know exactly what it was. And a parameter we always look at when evaluating the potential of a material for these applications is the width of the transition. So the width is shown here in this slide, is 6 gigahertz. And this is basically the bandwidth for quantum storage you are going to be able to use in the end. So in this case, is what we normally find in rare materials of this order of magnitude. Something, however, which is also interesting is when the lines are too broad, this indicates the quality of your material is not so good. It means there is a lot of defects which are provoking a lot of inhomogeneity in your material. And this is not the case here. So this shows that the molecular crystal is a very high crystalline quality. So something else I show in the slide number 16 is the population lifetime for the optical level. So there's 540 microseconds, and this is a value which is important to have in mind because it establishes the upper limit to the quantum storage. So the quantum storage on a transition can never be longer than the population lifetime. And so let's say this is our upper limit, which is something completely okay, let's say, to do a lot of things in this field. So if we move now to the section number 3, which is the really quantum properties of the material. So far it was just preliminary properties. When we want to prove that a material can be used for photonic quantum technologies, we need to measure the lifetime of the quantum states. This means we need to create superposition states in our transition and then measure how long these superposition states can live. And we do this by a specific technique we call the photon echoes. So this technique is very, very similar to a different spectroscopic technique used in magnetic resonance. So it's called the Hahn echoes. So even when you go to the doctor and do magnetic resonances, you are using this kind of sequences in your medical studies. It's something quite surprising for some people, but it can be used also in the optical domain. And it can be used to measure quantum states, as surprising as that can seem. So this is what we did in our lab. So in slide number 18, you see what is the decay of the quantum state lifetime done using this technique. In this technique, what we do is we increase the time we wait between these different light pulses. So it's basically a sequence of light pulses. And we separate these pulses more and more. And the more we separate it, the less signal we get in the end. And this is because our quantum state is decaying. So by fitting this decay, which is a typical exponential fit, it's nothing very, very difficult to evaluate, we obtain a quantum state lifetime of the order of 10 microseconds. So you can see that even when our upper limit, ideal limit, was 500 microseconds, the actual lifetime of the quantum states in the optical domain in this material are 10 microseconds. This is nothing very surprising, it's often the case, and this is because we have mechanisms around our ions which are limiting the lifetime of the quantum states, and this is because the ions are surrounded by other atoms which are creating sort of electrical and magnetic perturbations, and that do not let the quantum state to live as long as could if it was up to the population lifetime. So in slide 20, I show you an important figure of merit for these applications. Is we always going to compare the line width of the transition of the ensemble of ions in the material, and this was this 6 gigahertz I showed you before. So it's the bandwidth we can obtain, and we compare this with the line width of an individual atom, and the line width of an individual atom we can calculate from the lifetime of the quantum states. And this ratio in this particular case is of the order of 10 to 10 to the 5. And this is the number of qubits of quantum information units you could create in principle in this material, so which is indeed quite a lot. So, well, next property, this is very technical, is showing how the quantum states evolve at very, very long times. And this is useful when you look at single ions. So when you look at single ion, you're following your single ion, but your single ion transition could move with time because of perturbations which are happening at very long time scales. This phenomenon is called spectral diffusion. And this is also, we also evaluated. And if our quantum states lives of the order of 10 microseconds, we can still see that there are perturbations at very much longer timescales, like the millisecond, which are provoking some fluctuation of the transition. But this remains quite limited in this case. So in typical molecules, if we look at the organic molecules to compare, this spectral diffusion will be about 1,000 times more than what we observe in these rare ions. So this also proves that the idea of putting the rare earth ion in the molecular environment has advantages with respect to looking to a traditional molecule like organic molecules. So I move now to slide number 24, and what I present in this section I call the spin structure is the other property of the rare ions we want to look. So at the beginning in my introduction, I mentioned that one of the important points of rare materials is that we can have quantum states in the optical domain and also spin states, spin quantum states simultaneously. So which makes these materials quite unique. But in this new material, this molecular crystal, we knew we would have spin states, but once again, we didn't know which were the transitions, in which energy were the spin transitions. So we had to first probe the material to identify what we call the hyperfine structure or the spin structure. So we did this by another spectroscopic technique quite specific to, it's called spectral hole burning. And I'm not gonna go into the details of this technique, but this basically, the take-home message is this technique allows to manipulate the ground state population. As you see in my scheme, you see that there are several sublevels, which what I represent by the small balls that are equally populated. And with this technique, we are gonna be able to remove population from one of them and store it in the others. So that's what we call the spectral hole, is this absence of population in a particular level. And when we do this, and we analyze when we send light through this system, once we have done this ground state population manipulation, we see a very characteristic spectrum, which is shown in figure 26. And from this kind of spectrum, we can deduce what the hyperfine structure is. So what's the energy of the hyperfine transitions? So I move quickly into this. So we have some peaks we call the holes and side holes, and other peaks which call the anti-holes. I'm on slide 28. And by knowing where those peaks are positioned in frequency, so you see the scale of my figure is frequency in megahertz, we can resolve the hyperfine structure. So the hyperfine structure we find from this analysis is shown in figure 29. So you see we have two ground state transition, one at 21.5 megahertz, another at 34 megahertz, and two excited state transitions, one at 46 megahertz, another one at 37.9 megahertz. To prove that our estimation is correct, so we did a simulation in red in the slide number 29. You have a simulation of the spectral hole burning spectrum, and you see that the agreement is very good. So it really seems that this is the actual hyperfine structure we have. We can also evaluate the strength of these transitions. This is based on the intensity of the peaks we have in the spectrum. And this is given in a table. So the table is shown in figure, in slide 30, shows the strength of the different transitions from the ground state levels and excited state levels. So those transitions are not equal. So there are stronger ones and weaker ones. And this is also an important information later for quantum storage, because we are going to take advantage of the stronger transitions. Something else we can do with this technique of spectral hole burning is evaluating the population lifetime for the spin states this time. So before I show you the population lifetime for the optical states, and now it's for the ground spin states. So we do this by looking at how long time take this population to go back to initial level. So we start having all ground state sublevels populated. Then we redistribute the population until we have this spectral hole, and we wait. And when we wait at some time, we see that the ions decay back to their initial position. And by looking at this at different times, that's what it shows in slide 31, then we see how the spin population relaxes and gives us the population lifetime. So in this case, we see a behavior, dynamic behavior, which is pretty complex with different components. That's why the figure has different slopes in time. And we found the shortest component is 5 minutes. This means, the shortest component is 430 milliseconds. This means that if we put ions in a different ground state level, they can stay there for 430 milliseconds. So you see, this is much longer than in the optical states. And this is why the spin states are the ones we really want to use in the end for quantum storage. So basically what we want is to get the optical quantum states into the optical transition and then transfer it down to the spin states so that it can stay much longer time there. Something we also show once we had all these ingredients, that we know what our hyperfine structure is, how long-lived it is, which is our optical properties, and so on. So it's what I show in figure 32. So we did what we call a population initialization. So with optical pumping, we could remove ions from two frequencies, and this is the very two big peaks we show in figure 32. We have a figure of initialization where there are two deep holes, and this is because all the population is being transferred to the third level in the structure. And this is actually the starting point when you want to do quantum storage. You need to be able to remove your population from two states and to put it on the third one to start. And this may seem trivial, but it's not in practice, because this can only be possible if the lifetime of the spin states is long, as we have proved in the previous experiment. So to finish, I will end up with the most fun part of, for me at least, of the presentation, is that now, okay, we have proposed a material which combines two material systems, molecules and rare earth ions. And we have synthesized it, we have characterized it, now we know a lot of information about it, we have all its identity card. We can start to do some proof of principle of quantum storage, of real quantum storage. So for doing this, we use one of the most widely used quantum memory protocols in the field, which is called the atomic frequency comb. It's probably quite complicated to go into details of this protocol. What you should keep in mind about that is what we are gonna do is to manipulate the spin population in a way that we are gonna create a comb on the atoms. So we are having like a a little bit difficult to put it in easy words, but we are gonna, well, let's say it like that. So we are gonna create a periodic structure which is gonna be our base of absorption, and into this periodic structure we are gonna set our storage input pulse, and then the quantum memory. So this comb is gonna become the quantum memory. It's gonna emit back a pulse. So in the sequences shown in figure 33, indeed, the quantum memory storage is only the two green pulses in the end, very end of the sequence, while all the other things you can see, so what it represents as a pulse sequence, is the preparation of the comb. So I can show you how we do this experimentally. So in slide 34, I do really show you what it looks like experimentally. We look at the absorption, optical absorption of the transition, and we do a big zoom on this absorption. So the absorption is a peak, but if we zoom into a very small frequency range, we are gonna see like a flat absorption range. What we are gonna do next, move to slide 35, is to create a big hole, a big spectral hole. So the big spectral hole is shown in slide 36. And this big spectral hole is going to create a big anti-hole, which is what it is indicated on the red highlighted area. And it is there precisely on slide 37 that we are going to send our comb creation, and the frequency comb appears on slide 38. So you see this teeth. So this is a very small comb. We can do much bigger. So a big comb with a lot of teeth and larger space between the teeth. So we did a very, let's say, modest one for this demonstration, because we don't have the advanced equipment we would need to do a really very big comb. But anyway, a comb like this is even enough to really prove that we can do quantum storage in this material. So now we have created our comb in the atoms, and this periodic structure is going to absorb my input pulse on slide 39. So we send an input pulse to the comb, and we get the output of the memory. So this is shown experimentally on slide 41. So what you see on the right is the input pulse in blue. In the dot curve is what's transmitted by the material, and the red pulse, which comes after 0.5 microsecond, so a little bit before 1 microsecond, is the output of the memory. And this was the first time this storage protocol was applied to a material which was not a bulk crystal. So we have also taken into account that our molecular material is not a nice large-scale crystal. It's just a small slab of 500 microns, highly concentrated. So this protocol has been used a lot in other kind of materials, but had never been applied to such kind of material as we do here. So what I show in slide 42 is that if we modify our comb in the space between the peaks, we can modify the output of the memory. That's what's shown on the slide on the left. So the more space are my peaks, the later comes my output of memory. So this also further proves that this pulse coming out is out of the atomic frequency comb. And that was basically all I wanted to show you here today. A small summary to finish on slide 43 and on. So I have shown you that we have synthesized this compound, which is we call in the field stoichiometric isotopically enriched molecular crystal. Stoichiometric means it's fully concentrated in rare earth ions, and isotopically enriched means that it has only one European isotope. So this is the merit mostly of the chemists which did the material. Then we have measured its optical quantum properties, and this is what's shown here by the optical line width of 30 kilohertz, which is what I mentioned before, being 10 microseconds of quantum state lifetime. We show that these lines are not fluctuating a lot on time. That's what means they have low spectral diffusion. Then we studied the spin structure with this technique I call the spectral hole burning. So we did determine what the spin structure was, which were the transition frequencies, which was the lifetime of these levels. And finally, we did some state initialization or spectral tailoring and the atomic frequency comb optical storage. And of course, all the details are given on the Nature paper. So the final slide is a photo of the group I work in Paris, the names of the people working and the collaborators in this project in Germany. I thank you for your attention and welcome your questions.
Thank you so much for this really interesting presentation and that you explain to us your work, you know, in this detail, but also in a comprehensive way. So it's really wonderful. So thank you. And just for people to understand, like, how long did this work take? You know, until the
Yes.
publication came out.
Well, it depends a lot. In this case, it was about less than 1 year since the first studies until the publication, or around 1 year, I would say, which is pretty standard, but it can be much more sometimes. It can be less. It was in the middle of the pandemic we did this work. So indeed, I have to say that we had more time eventually to focus on this than we would have had with no pandemic, because of course many things were cancelled. There were no conferences, no teaching, no so many things, and it was maybe faster than usual. Thanks to that, if I may say, thanks to what was a terrific period, this pandemic. But in that sense, it was a bit helpful for go faster than usual, I would say, to do the experiments, then analysis, writing the paper, submission of the paper, revision, and publication.
Wow, that's very impressive. I thought it would be kind of longer, but that's really impressive. And also, your results are really good. So, do you, in the end, it will be really interesting for quantum computing and data storage, as you said. Is this using this? Will it use more energy or less energy with what we currently have been trying to develop for quantum computing? And from the I know, yeah, I don't know. Will it be like more energy um,
Efficient, you mean?
intense? Yeah. Hmm.
Mm, that's difficult to say because indeed these all of quantum technologies in the long term will work at very low temperatures. So the superconducting qubits are the ones at a higher degree of development, work in these huge cryostats. And these systems, maybe not such a huge cryostat, but still in also cold temperatures. And in that sense, they would have some energy consumption. We are definitely quantum technologies. Unfortunately, we are not about green technologies. But the idea is that we are having devices which are going to be so technologically advanced. We are not aiming at having like a lot of them. Like it's not like everyone will have quantum computer at home. No, it's not. I would say that's not what's the goal. Is we'll have few maybe, but will be extremely efficient, and we'll be able to do things and simulations and maybe calculations to develop new medicines and so. But will be few workstations, so will be expensive, will be time energy consuming, but that will be important for society anyway. It's like when we go to the hospital and we take magnetic resonance because we have an injury. This system is very high energy consumption, and it has liquid helium, and it's costly, but it's very important for our health. So, but of course, we don't have a magnetic resonance at home. There is the hospitals which have one of them. So I think quantum technologies are a little bit like that. And in this case, we'll see. It's difficult to say. I cannot really advance in terms of energy waste, to be honest, compared to what we have currently. I don't think it will be worse, but I cannot promise it will be better either.
Oh yeah, I'm sorry. Yeah, it wasn't meant to be a criticism or so, but maybe
No, I understood. It's a completely legitimate question, and it's important question to think about this.
Yeah, and I wanted to give Frank an opportunity to ask a question, so please go ahead.
Oh, sure. Thanks, Katrina. Thanks, Diana. This is very dense for
Yes.
hobbies like me of physics. So, but definitely congratulations on this amazing results. And I think the idea of combining two systems that each have distinct, unique advantages are quite, I mean, actually the team can carry through. So it's definitely a triumph, effort. You did it in 1 year. That's just amazing, right? So, um, so quick question on the just I guess I have so many, but limited by time. But
Yes.
in terms of education, that so you mentioned that I mean, what comes to my interest is the regarding the density part. So you mentioned the high density of qubits will be an advantage, but
Mm-hmm.
to have. However, it
Yes.
also somehow comes with a challenge that create bring in noise, reduce the lifetimes, isn't it? Or
Exactly.
so
Exactly. Exactly. Yeah.
you are comparing essentially the I would assume that the one on the left, i.e. the rare earth crystals, they are traditionally by bulk crystal, right? So in that sense, the meaning crystal. By crystal, we usually means that it's very orderly and well controlled. So yeah, just to
Well,
get your insights. Yeah.
exactly. That's the point. So the bulk rare crystals, they're very well organized, the atoms inside, but the rare ions are a dopant there. It's not ions, not lattice ions. Let's say they come in a small amount to replace other ions which are in the crystal, and by doing so, they end up being located randomly. So to say a typical rare crystal would be doped with rares of 1% or 0.5%, it means you have one rare earth and then the next one is somewhere else. But you have no deterministic control about where the ions are with respect to each other. And there is some initiatives to try to work on that, like what they call ion implantation. So instead of doping, what they are going to do is irradiate the crystals so that they can put the ions in particular locations, but afterwards there are some high temperature treatments done to the crystals and the ions diffuse. So the spatial deterministic localization is quite a big deal in these materials. And very often we work at extremely dilute media, so big distance between the rare ions. Basically, because as soon as we start to concentrate a bit, we have this quenching, we have this noise which appears. But in the case of the molecules, it's more. I mean, I wouldn't dare to say straightforward to locate them, but there is more resources to manipulate these materials and to create, let's say, 2D layers or play more a bit. If you change your ligands, maybe you just can tune a little bit, and instead of having 10 angstroms, you may have a little bit less or a little bit more. There's more tunability, which in the case of the bulk crystals is really not there, let's say. I don't know if this answers your question.
Yeah. So, sure. So, in what form that we're looking at your the samples you're working with that you're able to, is it two-dimensional like materials like
They are they are microcrystals, so they have there are several sizes. We obtain the sample in the form of a kind of powder, and when you look in a microscope inside, what you see is some squarish, well-faceted crystals which have a micron size. So we're looking at those kind of crystals, and typically we put a small ensemble of them. So we look at an ensemble of these small crystals. But typical rare crystal would be something like 1 centimeter long and maybe 5 millimeters, like a kind of cube or rod of 5 times 5 times 10 millimeters. So it's completely different size scale.
I see. So yeah, that's okay. So right. So the if I made that how should I understand the my next question? If so, how should I understand the Lorentzian shape of the absorption? Is it by Lorentzian? Is that a random type of collision type of results or?
No, so good question also. So the theory of line shapes establishes that depending on the kind of line shape we observe in these emitters in solids, we have some sort of type of defects. And when we have what we call 2D defects, like dislocations, or a crystal with big strain on dislocations, we typically going to observe Gaussian lines. And when we observe Lorentzian lines, we are more in a system which has point defects, like punctual defects, like, well, an ion here is missing, or there is a vacancy somewhere, or things like that. But it's to say the level of disorder is less when you have a Lorentzian line in general. So you have a better
So
crystal quality.
less than Gaussian in a way.
It's less than Gaussian, yes. It's, normally a Gaussian material is less organized, or to say has more structural crystalline defects.
I see. Yeah. So I guess, for this round, I'll just, the last question is, so the temperature
Mm-hmm.
you're working at is the very low, right? So 10K and 1K is that
Yes. Yes, right.
and so for the so isn't that if you have, so for me I tend to think that the organic environment like the frame so I'm just trying to see that the what causes the how could you improve even better improve the say so I understand the the lifetime and versus the line width is due to the kind of interactions with other neighbors, right? So I guess I'm coming back to my first question, earlier question again, that uh, are these due to their environment that you can change and even better improve, maybe even also compared to other available, maybe the bulk, maybe there it's better to control these things. I don't know, just a
I'm sorry, I
general
didn't
question.
understood. I'm not sure I understood the question. Is about the temperature, or can you reformulate it?
So yeah, so I guess I didn't ask a very coherent question. So the when in a main result is the of the work is the very high, very narrow like line width, right?
Line
So
with, yes, yes.
yes, so that means that it's the lifetime is long, meaning that there's there's
The
there's
quantum state
there's
lifetime, yes.
there's
Because in this,
less interactions in a way. So I'm trying to see how does that related to the environment for the, because
yeah,
environment we are
I got,
comparing
okay.
to environment, comparing the molecular organic versus the crystal. So one seems that a crystal at temperatures, same temperature, seems one
Yeah,
is more stable than the other. Anyway, so that's just
right. I got the question now. So indeed, yes. So the line width or its lifetime is long, but it still could be longer. So it could be longer if we could reduce perturbations with the environment. And well, for temperature, we in the paper I then show in the presentation there is the temperature dependence, but we could still gain if we go below. So we could go to millikelvin regime and we still gain a little in reducing the interaction with phonons, which is interactions related to temperature, to say somehow. But there is another contribution. This is also in the paper. Is not what I presented today. The fact of having the high density, and that not really of having the high density of ions, of the fact of exciting many ions at the same time with what we do in these experiments, also creates perturbations. So those ions which are excited, this high excitation density makes that they still interact with each other. So that's also another thing we could tune. Let's say we could tune it by either putting the ions farther apart from each other, slightly farther apart, or by reducing, working at smaller ensembles or with narrower excitation, or well, several things which could be done. And then we also have perturbations from the spins in the environment. So we have the proton, we have, well, carbons and isotopes have a little bit of spin. Here I'm talking about magnetic perturbations. So that would come back to modifying a little bit the atoms in the ions in the molecule by chemical means. So let's say replacing or doing this isotopically pure carbon for the synthesis, things like that. So by this, we would reduce magnetic. We always have 3 points to consider: so magnetic interactions, electric interactions, and temperature related. And these are the 3 things we could work on to make the lines even narrower or the lifetime even longer. Does this reply your question?
Yeah, this is a very. I do see this as very has huge potential. I mean, this field is fascinating. I guess if you have more time, I will ask you how to get into this field as a computer scientist or engineer, material engineer.
Yes.
Yeah, thank you so much. I don't know. We've been going for an hour, but if you want to answer Frank's last question, I'm fine as long as you have a few more minutes left. Thank
I
you.
do have I'm trying to get friends up the stage. I do see a few good friends down there, but I guess they're busy at this hour. So, I mean, all the friends in the room and the audience, feel free to come up and. This is very interesting research and rare opportunity to interact with the first hand creator of this research. So by the way, I want
Well,
to learn something about the so the memory part. So I understood partially of the comb and I understand the spin supposed to be longer because it's compared to optical. Since there are some sort of selection rule protected, right? So that once so why do you need two pits? What is the two? Let me see the slides. Oh, the slides. I guess I just ask random questions now. So, slides number 32. You have two peaks.
mhm.
I mean, you explained a little bit, but I think I missed it. Could you one a little bit more, spend a little bit more on this slide? So why do you need two for the? You have a plus and minus the ground states of spin half, and so that's what you want to initialize to, and then you pump it up, and with two, yeah. So yeah, I guess
No,
I'm curious of.
I am. Is this the initialization you're talking about? Is it? Yes.
Yes, yes.
I am not. I know. Yeah. Well, I am not surprised. This is visually not so easy. The difficulty here for the understanding is that we every time we manipulate the ions, we manipulate what we call different classes of ions. So since our ions are an ensemble, let's say, and they have relatively different transition frequency with respect to each other. This is what gives us this inhomogeneous line. Then when we send our laser, we are actually interacting with several transitions at the same time. So this makes the understanding of these figures a little bit difficult because we see many phenomena simultaneously. And what we do here is we do remove ions from two ground state levels for one class of ions out of 9. So the thing is, that's why the structure around is a bit difficult. So you see the two big holes. And what we prove here, so for the people who evaluate this work, is that the holes are very deep. So that's the 100% scale, which means that for these ions, they have really been fully removed because our material has become transparent or 95% transparent at that frequency. So it does not absorb light anymore. And this means the ions are somewhere else. They are stored in the level which is the third level, since we have 3 in the structure. But this third level is actually in the figure, but we see it is not so big. And the reason is because we are only seeing 1 ion class out of 9. But why it's important is because when you really want to store a spin quantum state, you need your 2-level system to be initialized. So 2-level system. Here we have three levels in the ground state. But for storage, you're going to use 2 out of the 3, and then the third one is going to be a buffer layer. You're going to use when you need to put things there for a pause sometime. But before any storage, you need to have the population in one of them, a single one of them. Otherwise, if you start to create superpositions, it's like doing nothing because if your system is not initialized, you have as many ions in the excited state as in the ground state, and this is when it cannot work. In the optical case, this is naturally like that, because in the optical levels, the energy is sufficient to have everyone in the ground state anyway. But in the spin states, even at very low temperature, all these levels are thermally populated. So they are all populated. And then you really need to initialize them. To be able to initialize them means to be able to create this full transparency, and so that the ions are somewhere else. And this is only possible because the population lifetime of this level is long. Otherwise, you could pump them, but immediately they would come back. And this is what happens in many solid state systems. And that's also why we can create the COM. These COMs in the quantum memory protocol can exist because, again, when you see the teeth, is because there is ions which have been removed periodically at those frequencies for some time. And then you can do your whole sequence for some time, and the ions don't come back because the population is long where you store them. I know it's a bit difficult, this part. It's to transmit the easy image of it.
Yeah, so I think you did thank you for that. The good jobs for, at least for me, to get a little bit transparency. Maybe not say 30%, 70% still opaque. But so I do get the part, the spin, the nuclear spin ground states are thermally populated, even at a very
Yeah.
low temperature. And
Yes.
so for your initialization, you would need optically pump. I mean, somehow get those up to, move them away, right?
Exactly.
So,
Yeah.
and they stay there due to their
Exactly. You move
long
them away,
lifetime.
and you want them to stay there where you put them. And this is what is not always the case. So when you manage to do that, is you say, okay, this material can do that. So it's necessary for whatever goes afterwards to start by that.
I see. Okay. Okay. Thank you for that. So it's yeah. So I do see, I can see that this is I don't know if it's your figure. I mean the figure Mary that here you listed 5.5 Is that the record holder? Is that the why nature becomes so fascinated with your work? So I don't know how long are we looking at in the future,
Well,
and what
if
is there an
you
industrial?
if you look at European in the very best environment, like a best rare crystal you can find, then the spin states can live for 23 days. So you can put them away and they can stay 23 days. So we are very, very far from that in this case. We don't need that long either anyway. That's almost a curiosity. But the spin states in rares are very, very long lived in general. What was, I would say, why this paper was highlighted is because the optical quantum state lifetime, these 10 microseconds, is between 3 and 5 order of magnitude longer than what you can observe in molecules. So it's that the main point, and is that which allows to do an optical frequency comb storage, which you could not do with a molecule, for instance, an organic molecule, and you can do here. But if we compare to best bulk rare crystals out there, there is a big range for improvement, of course. But there is all the chemical engineering to start playing around and see how we can optimize and lengthen and so on.
Got it, got it. So yeah, I misspoken. Yeah, it is the optical that lifetime. Is what the main achievement
Yes,
here. Yeah,
exactly.
I got
Yes.
you. So yeah, the spin state. See, when you put it away, when you say by days, you still need to keep it in low temperature or no, or the spin
Yes,
just
of course.
frozen.
No,
Oh,
no, no,
okay.
no. You have to be at low temperature. As soon as
Okay.
you increase in temperature, you start to have fast relaxation mechanisms. Always low temperature, yes.
Right. So I guess my last question for now is could you mention a few, I mean, maybe potential like downstream collaborators. I would assume that with the qubits, the quantum computing manipulations with, for example, spin and I mean the qubits in that.
You mean scientific collaborators in here, or I get
Just,
you?
just,
Or
just in general, I mean, you say in your application section of the paper, you probably mentioned that I mean, your new finding discovery can be applied, or there might be potential interest in applying your. Of course, you mentioned that this is a family. You know, there's already bulk crystal technologies, but with the new molecular um, microcrystals, I mean, say easier to manipulate, higher density, would that be
yes,
a
okay,
strong
I
interest
see
from
that.
the user
So
group?
there is for especially for quantum computing. So when you want to do quantum computer, you need quite some qubits. And if you gonna do that with optical transitions, so through optical transitions, it's not like we are not using the spin, but using the optical as access. The way it's approached in the rare community is by coupling two cavities, two optical cavities, and be able to manipulate single rare ions. Let's say, so I have my quantum computer and I have photonic system around, and then I pump this ion, and then another ion is qubit number 1, qubit number 2. I make them interact and so on. And this is in practice very, very difficult to achieve in bulk crystals, first of all, because these cavities have very small volume, so you cannot fit a bulk material in there at all, so you really need to go down to some nano or micro system, which, by the way, we also try to do. It's another of our research lines with traditional rare crystals at the nanoscale. But in addition, if you want to do these gates, you would like to know, as again, this goes back to this localization. So the potential is more for scalable system. So red crystals nowadays, when you work at single ion levels and so, but something is done, it's challenging. People work hardly on that, but you have one ion, and it's very difficult to have one and then another one and then make them interact with the cavity and everything. So we believe these systems are gonna a little bit reduce the technological difficulties of doing that. The principle is the same as with the rare crystals, but the coupling to resonators is expected to be less challenging because like, there is a big community on single molecular spectroscopy and so on. These materials are not obtained at very high temperature, and this is a very big issue for when you want to couple these two photonic resonators, because typically you need to heat your material to more than 1000 degrees to get good properties, and this will destroy your photonic structures. These molecular materials are obtained at low temperatures, so in that sense there's no limitation on that. So it's really in that sense, and be able to couple the system and then be able to control more than one ion and scale up to qubit, to a useful number of qubits, which currently is difficult with bulk systems. Very, very difficult.
Yeah. Oh, go ahead, Frank.
I just want to say that's amazing, great potentials. Yeah. Go ahead, Karina.
Yeah. Yeah. My last question is so what are you working on now? Like, what's next? Are you looking for more different materials, type of crystals, or are you looking into
Right.
yeah.
So on this particular project, there is material development ongoing on trying to customize a little bit more the molecular structure. There is also the project of looking at other rare ions instead of europium, which have a better wavelength for applications, or which can have the hyperfine structure, the spin states have higher energy, and this is better if you want to couple to superconducting qubits, for instance. So I would say those are the main lines. So we're looking at at other rare earth ions, what we call the paramagnetic rare earth ions, like erbium, ytterbium, which are another subtype of rare earth ions. So europium is a non-paramagnetic rare earth ion. But those paramagnetic, they are more easy to be perturbed even than the europium. So they are a bit tricky. So they have to be handled very carefully. And then, yeah, they really try to optimize the molecular structure, looking at to other molecules too. So we already have looked at other molecules, and there are some which indeed perform much worse, others better. It's a huge family of materials, so there are too many things to consider and to screen a bit which cases can be interesting, which not. So it's really the beginning, I would say. And there's other projects in parallel, of course, that I'm working on too.
Yeah, that's really interesting and exciting. And just one last one. You said in some you can extend the time to 23 days. So are these rare earth materials also candidates for batteries that you can, we had the room about if you use a quantum battery system that you can charge like, a Tesla battery in like 3 minutes instead of like 10 hours. So would these materials, would they be candidates to use them for batteries, but for, very high, not for everyday use people, but, for batteries where you really need to charge very, very fast?
Well, I'm not quite sure. But I would guess not really. It's a very different property when we look at batteries of energy storage. Than we don't have a power release in these quantum memories. We store quantum states, but for a battery you need to store power and deliver power back. So, well, it's not at all my field, I have to say, these batteries, but I would guess not quite.
Okay. Thank you for clarifying that. And thank you so much for coming and taking the time to answer all these different questions. We really appreciate it, and we wish you all the best and a lot of funding for your research. It's really fascinating, and if you have maybe one day like updates on your research that you have time to share, please feel always invited to come back. Thank you so much, Dan.
Thank you. Thank you for the nice discussion. Bye bye.
Yeah, thank you, Diana. This is our room usually have a more audience, but I guess it's due to the particular hour. So yeah, I guess there's a replay, and I think that your research will be greatly appreciated by our frequent audience. Yeah, and friends. Yeah.
Yeah, well, thank you. Thank you for giving me to discuss this, and maybe see you in the future. We'll see.
Yes.
Yeah,
Bye
please do
bye.
come back.
Yeah, please to come back. And thank you so much everyone for coming. We have this week more rooms coming up. Um, on Wednesday we have Nick Horner. He will talk about sea sponges and how they sneeze to dispose waste, and some more marine biological research that he will share. And then on Thursday we'll have Dr. Tarduno talking about the origins of the inner core structure of our Earth, which is paleomagnetism. And then on Friday we'll have Dr. Valtteri Wikström talking about inter-brain synchronization during online gaming. When people are far apart they can still their brain activity still synchronizes, which is really interesting. So yeah, thanks for coming. I hope I hear you all back soon. Bye everyone.
Bye, Karina. Thank you. Thank you for the organization of this wonderful
Yeah, thank you, Frank, for
meeting.
asking interesting questions. It was interesting discussion to listen to. So thank you.
See you next time.
See you. close the room in 3, 2, 1. Bye, everyone.